Firstly, we talk about primality tests and connection with the modular arithmetic. Do you have any subjects with algebra and number theory? Okay, and you know what is the Fermat-Little theorem? So firstly, we remember modular arithmetic. And you remember what is a set. Yeah. What is it?
It's the set for all the integers from 1 to n.
From 0 to n. To n minus 1 usually, because
Number 3
from 1 to n.
yeah, so it should be still n.
Okay.
Oh no, it's from 0 to n. It's modular.
Yeah. And you remember that if n is prime number, then what we know about this set? You know what is the field? And you know that Zn so is the field. It means that for every integer that is not equal to 0, we can find such x that a multiply x equal to 1. Yeah. Okay, so what we want to know. We want to know when integer number n that we get from the inputs is the prime number. And in this way, we can use this property and some corollaries from this statement. And what is the Fermat-Little theorem?
It's m mod.
If n is prime and a is such that, do you remember what is this parenthesis equal? It is general common divisor of two numbers a and n. And if it is equal to 1, then a in a power n minus 1 equal to 1 mod n. Remember it, yeah? And do you know the proof of this theorem? No? Okay. In more general way, there is Euler. If n can be integer number without 1, and a is to integer such that general common divisor between them is equal to 1. And do you know what is the Euler function of n? Not prime numbers. Numbers such that that equation is true. Yeah, that is had only one as common divisor with the n. Yeah, it is x from 1 to n such that the common divisor between them equal to 1. It's Euler function. So, and the consequence from these conditions is that A in power phi of n is equal to 1. And of course, for prime numbers, we have that phi from n minus 1. Is it understandable that, yeah, that every number from 1 to n minus 1 is holds this equation, yeah, and then we say that this function is equal to n minus 1. So Fermat-Little theorem is a corollary from this theorem. And did you face with this theorem ever? Yeah. And do you know the proof of it? Proof. Yeah. Yeah. You don't remember. Okay, and do you know what is the order of the elements modulo n? Order from the elements A modulo n. It is minimal m such that A in m, A power m is equal to 1 modulo n. You didn't face with it. Okay. So firstly, we can prove that for every A between n and between 1 and n, order is the finite number. Do you know how to prove it? For example, Dirichlet principle. Do you know what is it? We have only finite number between 1 and n, so we can find two different E and J such that A in power e is equal to a power g. Yeah. So, for example, if e bigger than g, we can divide it by a in g and say that a in is equal to 1 modulo n. So it is one of the such integer numbers, and so this set is not empty, and minimum is minor or is less than plus infinity. Is it understandable? Yeah. Okay. So it is the end of the proof. If we try to understand what is the set a in integer power, we find that it is finite set such that number of integers is equal to order of a. Of course, we say that two numbers in this set is equal if the difference is equal to 0 modulo n. And how to prove error theorem. Firstly, we say that A it is a finite subset of this set. I define it like U. And then if we find, and I define it like A with the index 1. If difference between these two sets is not empty, for example, some y we can find here. Yeah. Then I define a y as a number such that it is y multiply a power 0 multiply a power 1 y multiply power 2, etc. And we know that this set is finite, then this set is two finite. Yeah. So then we repeat this motion. Yeah. And find that U is equal to some subsets. Yeah. And we can prove that these two sets, these two subsets, are not intersecting. So I said this union is as disjoint union. Yeah, you understand these square symbols. And then we see that number of U. Oh, yeah. And it is how to prove n-1, how to prove Fermat-Little theorem at the first point, and then I said how to prove error theorem as a common way to this proof of this proof. So we said that it is n-1, and then we say that number of integers from 1 to n-1 is equal to n-1, and we know that in A1 we have ord n from A numbers, and if we have k subsets here, then we say that n-1 is equal to ord n from A multiply k, because the number of elements of these subsets is equal to A1. Yeah? And then we say that we can divide n-1 by order of element A. And then we say that A n-1 is equal to A ord power k. Yeah, it is equal to 1 modulo n, of course, because we know that order of elements, by the definition, it is such m that we have this equation. And so it is equal to n power k, of course, or 1 power k, and of course it is 1, yeah? It is a proof of Fermat-Little theorem, and in common way we can redefine U as the number of from 1 to n, such that their general common divisor with n equal to 1. And then we get here not n-1, but area function from n. And then we have these steps, this similar to these steps. Yeah. But here we find it replace with phi from n, because it is the number of integers in this set, in U set, by the definition of phi of n. Do you remember what is the definition of phi of n? Yeah. Yeah, it is, we can set like number of it. So it is the proof of error theorem, and as a consequence of it, we have some multi-tests. Firstly, Fermat's test. It is based on Fermat-Little theorem, of course, by the name of it. It is understandable, yeah. and it is a probability test to understand if we have a prime number or not. What is the working of this test? Firstly, we have an integer number. And we want to know, is it prime number or not? So, secondly, we find we get one number from 1 to n. N minus 1, yeah. It is variable number. We didn't choose some number. We say that it is random number from these numbers from this set. And thirdly, we compare a power n minus 1 and 1. And there are two ways. If it is equal or not equal. In which way we know differently what is the n. What is the n? Prime or not prime number? In this way or this way? No. When it is not equal. Because we know that for each prime number n, we get equal numbers here and here. And if we find such a that it is not equal, so we say that n is not prime number. Definitely n is not prime number. Because for every prime number, we have equation here. Yeah. Is not a prime number. But in this way, we say that n is prime number. But in some case, we get it wrong. So we say that it is not deterministic test. So in this case, we have probability. Do you have probability theory as the course? No?
Just comment.
What?
Only comment, not it.
And do you have in program probability theory in next semester? We have probability bigger than 0, that we got wrong answer here. Because there are some composite numbers, composite integer numbers that we find a that it will be equal, a in n minus 1 will be equal to 1, but n wouldn't be the prime number. Do you need example of it?
Or maybe a number is not
Prime, but we say as a result that it is prime number. Mm. 1 second, please. Okay, for example, n equal to 3. Oh, no, sorry. It is prime number. Yeah. So yeah, for example, 15 and a equal to 2. It is not a prime number. Yeah. But if you try to is it equal to 1? It is not equal to 1. Yeah. Okay, yeah, I find the example. It's equal to 4. Yeah. If we try to multiply 4 by itself 14 times, we get it is equal to this number, this, and we get 1. And in this case, Fermat test as the output said that n equal to 15 is prime number. Okay. And
A cannot be 1 because if A is 1, it also fails. If A is 1, it also fails the test.
we need to say something about n, that it is prime number or not. So if of course we can say in this way that we don't know n is prime or not, but we have probability to get wrong, not that it is not equal to 1 here. So so of course in most cases we have a right answer here, but we want to find other tests such that we get wrong answer in less cases. And for example, there is second test with the name Robin Miller test. Or Miller without second L. Firstly, we say that we can represent if n is an even number, it is not prime, yeah, and it is bigger than 2. So firstly, we can say that if n is even, it is not prime and bigger than 2. Yeah. So if it is odd number, we can say that n is equal to 1 summary of 1 and this number, where d is odd. Okay?
S is
S can be integer number that bigger or equal to 1. For example, for n equal to 15, we have equation 1 plus 2 multiplies 7. Yeah. And in this case, s is equal to 1. So s is one of the integer number. And in this case, we have some a such we repeat two steps from the previous algorithm. Yeah, we find random A. And of course, we can compare common divisor of A and N with 1. Of course, if it is not equal to 1, we have prime number N, because this number will be divisor of N is 2, and so it is not prime number. So, if we have this equation, then we compare A and D and 1 model N. And if A in power D is equal to 1, is not equal. So we say that N is not prime. If they're equal, then we compare a power to power r multiply d and minus 1 model n, and s will be between 0 and sorry, r will be between 0 and s. If we don't find such error that we get equation of it. Sorry, it is equal, but it's not equal to s. If we don't find, we say that n is not prime. And if we find, then we say that n is prime. And as in the previous case, we have some probability to get wrong here, because there are some numbers such that if we check these two equations and say that in S prime it will be a composite number, not prime. Firstly, about it is all about this test, and in this case we say that if we find such error that it is equal, or if a power d is equal to 1, in this case this equation is true. We say that A is the witness of probability of n. Or if all of them is not equal, it is witness of compositeness of n. So it is only about definitions. If you face in the future with the witness of compositeness or witness of primalities, it is equal to sum of equations such that these equations. So do you know in which algorithm we want to get prime numbers? For example, RCA. Do you know what is RCA? Cryptography algorithm to send some messages with some open and close keys. If we have A, it is the message. Do you remember it? Other students said that you face with it in the other course. For example, in number theory. Yeah, okay. So in this case, we want to know a very big prime number. And if we try to find prime number, we can use these tests, of course. Or in other cases, if you need some prime numbers, some big prime numbers, you can check consequently if n is prime by these tests. Okay? But of course, you have probability that you got wrong answer, and you need to understand it. Okay. It's about tests connection with number theory, and now we can have break time and then continue with other topic with the complexity classes. Do you know what is the P and P classes? XP, exponential classes. Oh. Such P, NP, XP. Firstly, deterministic. If you try to find some algorithms that solve some tasks, we face with some boundaries, and so we talk about classes as the boundaries of our algorithms, about boundaries of computational possibilities of the computers, for example. Yeah, because we don't have infinite resources for solve any problems. We have only some computers, some mathematicians, yeah, and we need to solve it. So firstly, first boundary, it is polynomial times. So if we have only polynomial times to solve some problems, we say that this task is solved in P class. Yeah. Interesting. It is class of tasks that are solvable with polynomial time. And a lot of tasks that we talk about it in our course is P task. Yeah, for example, finding the shortest paths between two vertices. For example, to find the longest substring with some property. In most cases, I think. For example, any tasks connected with the dynamical programming. Yeah, it is polynomial, and in most cases it is square time tasks, yeah, or linear time. So we talk about it a lot. Next class, it is XP time. it is exponential time. And for example, and we of course face with some tasks that we don't know is it in the P class or not, but we know that it is in XP time, and we know some tasks that is XP complete tasks, so it is very hard tasks. For example, I can say that chess, yeah, you know what is it? It is XP complete task. It means that, for example, if we can solve chess with, for example, if we can solve it with polynomial time, then we can solve any task in exponential class, XP class, with the polynomial time, for example. Yeah. So yeah, it is XP complete task. Or for example, Sudoku. Do you know this game? Sudoku, yeah. It is 2 here. And of course there are some other classes, but they're all in R class. It is solvable with finite time. And do you know some tasks that is not in R class? Did you face with the universal Turing machine, for example?
P versus NP?
It connects with it, but there is some construction, and did you face with Turing machine in other courses? Turing machine? No? Turing machine, it is model, mathematical model of computer. What it means? You have infinite string. We talk about it when we talk about finite automatas. Yeah. If we have some finite automaton, here, and we have infinite string with some characters. So informally it is equal to Turing machine. Yeah, it is a string with some characters and finite automata in it as a computational instrument. with some characters here. And there is universal Turing machine. As an input, we have we know that if Turing machine it is some mathematical model, we can express it with binary string, fine binary string. Yeah. So input as the input of it, we have M, one Turing machine, and words S. And output it is yes or no. It is the answer to a question if Turing machine M will stop in finite time if we put S in M. If we start M with the string S, then it computes something, and we want to know is this computer or machine will stop in finite time. If M is finished in finite time with initial string equal to S. And in common way, we don't know what is the answer. In common way, we have we don't know if we have some expression of Turing machine and some string that we got the right answer in finite time. So universal Turing machine is out of these classes. So there are some deterministic classes that connected with boundaries for time. Yeah. And there are some classes, of course, that has boundaries for space, time. We don't talk about it now, but you can express, you can write as a remark that there are some classes with restraints to space using for example L, B space, sorry, XP space. Let's try. And second point of this chapter, it's about non-deterministic classes. And first about NP. And it is tasks that are solvable in polynomial time using non-deterministic Turing machine. I didn't write it, but in first part of this topic, we mean that, we mean here that we use deterministic Turing machine. Yeah, it means that we use only deterministic algorithms, for example. Yeah, as you remember, when we talk about some graphs or algorithm on the graphs, we say that we have first step, second step, etc. Yeah, we have a deterministic algorithm to solve tasks. Yeah, but in some cases we have non-deterministic algorithms as you remember, as Fermat tests, for example, but that is true for every input number. And for example, some coloring problems, for example, if we have some graph, we want to know, can we color it with, for example, 3 color? Yeah? With red, blue, and black, for example, colors. And in common way, it is NP complete task. Yeah, because how to understand what is NP? What is a non-deterministic Turing machine? It is equal. Yeah, this definition is equal that we have some function. It names as verificator. And as it certificate, such that if x is in L, yeah, because of course when we talk about tasks, what we mean about task, yeah, what we mean about for example coloring problem. we want to know if we have graph. We want to know is this graph can be colored with 3 colors, for example. Yeah, and then it divides set of graphs into 2 subsets. Yeah, one subset with the answer yes, and one subset with the answer no. Yeah. So when I write L, it means that it's shortly language. It means that I write it is set of, for example, graphs or strings or other objects with the answer yes. Yeah. For example, in case with the coloring program of graph, it means that this set it is the set of graphs that we can color with 3 color. So if x in S, there exists S certificate such that it is equal to 1. For example, let L will be such graphs that has Hamiltonian cycle in it. Do you know what is it? Yeah. It is cycle that go through all vertices. And for example, S here will be null cycle. And verificator will check is S is truly the Hamiltonian cycle in graph. Yeah. We know that for every x from this set, for every graph, for every Hamiltonian graph, we can find Hamiltonian cycle, and it will be and verificator say that yeah, it's true that it is Hamiltonian cycle. Yeah, it is true that we have S in as the Hamiltonian cycle of G. Yeah. So in this case, this language will be in NP class. And in this case, of course, we can write that P class in NP class. Yeah, but we don't know if every non-deterministic algorithm can be can be reducible for polynomial time, for solvable task by polynomial time with polynomial time by deterministic Turing machine. So it is open conjecture that P equal to NP or not. And of course, there are a lot of articles every year that try to solve it, and then in some time scientists find contradictions in it, and so there is no one writes article about equality or inequality of these two classes. And for example, there are some cryptography algorithms connected with the number theory that works only due to absence of proof of this equality, because if we understand how to why it is important, why it so proof that P equal to NP, because there are some languages L that we say as the NP complete languages. Do you know what is it? NP complete. It means that there are in NP class A and Z NP hard task. So L is NP complete language if it is in NP class and it is NP hard. What is NP hard? It means that all L in NP can reduce to L. For example, for example, we have a task find the maximal cycle in the graph. L shift finds the maximum and we have L from previous example. Then we say that if we solve this task, we can check if this cycle contains all the vertices. So firstly, we solve L. And then we compare, we check if maximum cycle contains all vertices. If it contains all vertices, then we say that graph is Hamiltonian. Yeah. Otherwise, we say that it is not Hamiltonian site or Hamiltonian graph. So in this way, we can reduce some problem to other problems, to solution of other problem. And perhaps it is such problems that we can any other problems from NP we can reduce to this language. And for example, NP complete tasks. It's resets problem or only start. For example, you have Boolean formula with 3 operations and or inverse function. Yeah, and you try to understand is its formula true in some outputs or not. It is NP complete problem to find. Or for example, any colorings. For example, if you have as inputs number k and graph g, and you want to understand if we can color graph with k colors. It is NP complete task too. Or for example, finding combinatorial cycles. And for example, as games, Tetris is too NP complete. It's interesting that some games is very strong to solve in common way too. For example, Tetris. Yeah, and if we find, it's interesting that if we find polynomial solution for Tetris, we can find polynomial solution for every NP languages, NP tasks. It's interesting, yeah. And of course, there are XP complete, for example, tasks that is similar to this definition. Yeah, XP complete tasks is tasks from XP and such that they are XP hard tasks. Yeah, that all tasks from XP class can be reducible to these tasks. Yeah. And for example, chess is an XP complete task. Yeah. So you can face with very difficult tasks in games too. But of course, you can face with it in science, yeah, in in research of, for example, graphs, yeah, and or for example, Boolean formulas. So I think it is answer for questions why we have a lot of articles about graphs, about Boolean algebra, yeah, because there are some tasks that are difficult to implement and solve in computer because of very big, very high spending time on it. Yeah. Because if you try to solve it by some algorithms, we face with restraints of our computers. So in this case, of course, if you face with some tasks in the future, firstly ask yourself in which class this task is placed. Yeah, because for example, if you face with some task that is placed here in XP class, then you can say that okay, we cannot solve it because it has exponential time and we don't have such computers that can solve make milliards billions of operation per 1 minute, for example. Yeah, and then we try to solve this task approximately, for example. Yeah, for example, such task you can face in optimization problems, yeah, such as transport optimization problems. So it means that in, for example, industry, if you go to the company or start your startup, for example, yeah, you can face with the restraints of the computers because of complexities of tasks. So before you try to implement some code, yeah, ask, can we solve this task in polynomial time? Can we solve it in linear time or square time? Yeah, because if we can't, then we need to solve it, for example, approximately. Yeah, and we talk about it when we talk about, do you remember, networks algorithm, Ford-Parkerson algorithm? Yeah, that, for example, if we have transport system and we want to find the shortest path between 2 points, okay, we can try to use some algorithms that we talk about in our courses. Yeah, but if we have very intensive service with a lot of followers, yeah, if we have very big network, it spends a lot of time, and you don't have servers with such abilities to solve it. So you try to find not the optimal path, but approximately optimal path between 2 nodes. So I think in other courses you face with it that in one moment you solve not the tasks, but you solve, you try to find approximate algorithms that solve your task not precisely, but very nearby. Yeah, is it understandable? We can draw it like, for example, if you try to find the minimum points, yeah, and you start with 1 point on the wall.
Random point?
Yeah, random point here. And you don't know analytical function of this wall. Yeah, you cannot. You can ask, for example, what is the gradient here? You don't. Do you know what is gradient? And there are some stochastic solution of finding extremum, but in most cases you cannot find the right point. But for there are a lot of algorithms such that in finite time you appear in very small neighborhoods of these points, and it means that you cannot find the extremum of this graphic, but you can find the point here that will be where not so that will be very close to extremum. Yeah. So I think it's all about complexity classes. Do you have questions? So I think that's all. Next time we talk about marks, and it's about Мы где-то через 10 минут уже, этим 5-10 минут и все. Наша Клара, мы просто пораньше закончили, потому что мы все успели уже. Yeah. What is the NP hard? NP hard. Okay. For example, you can reduce some tasks to other tasks. And if you can reduce all the tasks from NP to one task L, we say that this task is NP hard task. For example, we can reduce all the tasks from NP to tasks if some Boolean formula with 3 operations is equal to 1 or not. So it is when it is when we say that language is NP hard. And if we have language that is NP hard and is in NP class, then we say that it is NP complete task. Because of course there are some exponential tasks that will be NP hard, but there are not in NP class. Yeah, we have NP, and it is an XP timer. Yeah, and we can find here some languages that is NP hard languages, but not in the NP. So these languages is not NP complete. It's about difference NP complete and NP hard. Yeah, because if you have language that is NP hard but not in NP class, it won't be NP complete language.